In this video, we are going to take a look at computing the volume of a solid that is bounded from above by the cone with the equation z equals square root of x squared plus y squared, and from below by the xy plane, which hopefully you remember has equation z equals 0, and then laterally, which means from the side, by the cylinder x squared plus y squared equals 4. So first of all, just to discuss what these things represent. Now, when they give you from below, from above, they're actually giving you the inside limits. So the below limit is going to be xy plane, which is z equals 0. Okay, so then you put that here. And then above is the cone. And then you put the cone equation over here, except since we're going to do this in cylindrical coordinates, we're going to need to change the variables. So my open math is complaining because it is not expecting you to put anything in x and y, because the variables in cylindrical coordinates are z, r, and theta. Now, to graphically represent what is going on here. So what we have is the bottom is the xy plane, and this is just a cylinder, right? So the cylinder, the difference between a circle, x squared plus y squared equals 4, which is just what you see on the left side, which is a 2D situation, and the corresponding 3D figure, it doesn't have a z, right? So now we have the z extra component, but the equation stays the same, x squared plus y squared equals 4, which means that z is anything. So this is where you just move that circle up and down, and then you get the cylinder. But it is bounded below by z equals 0, so it's not going to continue all the way down, right? So this z equals 0 is going to bound it from below. And then the cone with the equation square root of x squared plus y squared, that would be bounding it from above, right? So it's between like what you see inside the cylinder, but above the roof is sort of weird, right? Like a cone roof, and the bottom is, regular. Okay, so how are we gonna do this? So again, let's go with the setup first. The first thing you do is, again, the inside limits. Okay, so this would be the z limits. Okay, so then it's going to be dz, dr, d theta. And again, they tell you what they are. So they're saying below by xy plane. Well, xy plane has equation z equals 0, right? And so that's going to be your bottom, because it's always bottom surface to the top surface. And then above is going to be by the cone. So the cone is z equals square root of x squared plus y squared. But remember, these are cylindrical coordinates. So what do we know about cylindrical coordinates? So in cylindrical coordinates, we have the whole bunch of connection between them and the regular coordinates x, y, z. So what are the connections? Okay, so first the x and the y look exactly the same as they did for polar. So this would be r cosine theta, r sine theta. And z is just the same. Z stays the same. Z is z. So cylindrical coordinates are just a natural extension to 3 dimensions of the polar. So if you remember, because of the trigonometric identity number 1, x squared plus y squared equals r squared. And that was true for polar, and that's also going to be true for cylindrical. So when I see this kind of cone, square root of x squared plus y squared, to convert it, I use this connection. So I'm just going to have square root of r squared, which is just r. Okay, so that's going to be my top limit. So it's not going to be that square root, it's going to be r. All right, and then the other two limits, which is the r and theta, are just like polar. So think about what is the projection of this thing on the xy plane. The projection is going to be this circle, right? So imagine you just like flattening this thing so that it gives you the projection, right? And it's going to splash on the ground at the circle. And how do we set up limits at the circle? Well, we know how to do that using polar. So the theta, because it's a whole circle, is 0 to 2 pi. And then the radius here was from the circle x squared plus y squared equals 4. That means the radius is 2. So it goes from 0 to 2. So if you don't remember how to do that, go back to the polar coordinates section and look at that. Now, the next thing we need to figure out, so let me just already fill these out. We need to figure out, okay, what are we integrating actually here? Now, whenever they say find the volume, so use triple integrals to find the volume. The idea is that triple integrals are used to find the volume if you integrate 1. So your integrand is going to be 1. So this is going to be 1, okay? However, yes, it's going to be 1. That is if it was xyz, the regular coordinates, the rectangular coordinates. But what if it's, well, it's not polar, it's cylindrical. You should remember the pirate. Remember, the pirate says R. So you've got an extra term that seemed to come out of nowhere, but it's not nowhere. It's because we're switching from XYZ to R theta Z. And so you have to insert that extra R there. You have to do that, okay? Because otherwise this is going to be incorrect because you'll forget what's called the Jacobian. Okay, now we have to evaluate the integral. And the first thing I want you to ask yourselves, can I just split this integral right away? So the formula or the prescription for splitting is that your integrand must not have any pluses, minuses where you add in the variables, they're different variables. It's just a product of factors, something that has z only, something that has r only, and something that has theta only. Or maybe just some of them, because you can think of one as being the other factor. Now, also what has to happen is the limits must all be numbers. However, in this case, when you look at this right here, this is not a number, that's a variable. What that means is that you cannot split this integral right away. You must first integrate the inside integral, the z integral. And then once you do that, then you can split. So let's go ahead and do that. This is not going to be hard, but I'm still keeping the outside and the middle integral. So this is just r integrated with respect to z. So remember, when you integrate with respect to z, r is just a number. So how do we integrate a number, for example, with respect to x? We multiply it by x, right? Because derivative of kx is k. So this is what's going to happen. So now we're integrating r with respect to z. So this is going to be the number, the r, multiplied by z, right? And then we're gonna draw a vertical line. Now here is also very important to do what? So is it okay to just put 0r? Well, the answer is no, it's not okay. And I would actually take off points if somebody just does that. Why is that? Is it because I'm mean? No, it's not. I'm actually a very nice person. But the reason why I do that is because it's not clear for which variable you are substituting things, because you now potentially have 3 different variables, okay? So now, because the z is the inside and you were integrating with respect to z, you have to put z equals 0, z equals r, okay? Now let's go ahead and do that. So all of this, we're just gonna separate. And when we got 0 to 2 pi, we had 0 to 2. Okay, so it's going to be r multiplied. So first I substitute the top limit, right? So that's going to be r minus substitute the bottom, which is 0. Okay, and then I still have dr d theta to integrate. Okay, so to simplify this part right here, note that that's just going to be r multiplied by r, and that's just r squared. At this point, you absolutely can and should split it, because there is no theta here at all. So if you can think of the theta part, theta factor is just being 1. So this is just going to be 0 to 2 pi d theta multiplied by 0 to 2 of r squared. And now you have a product of 2 single integrals that you can easily integrate. So the first one is just going to be theta, substitute 0 to 2 pi. This guy is going to be 1/3 r cubed, substitute 0, 2, and then you multiply the two answers. So the first answer is 2 pi. The second answer is going to be 8/3. So the final answer would be 16 pi over 3. So let's check that out and see if that is correct.